Good evening and welcome to this class where we are talking about the spectrochemical methods. And our basic intention was that how we can use a spectrometer or a spectrophotometer to monitor a particular acid base reaction. Say the first example what we can think of is a typical acid base titration reaction, and in other way also we can consider this particular reaction as a titrant analyte reaction. So we have to use a particular solution of known strength, say a titrant volume, where we will utilize the analyte or identify the concentration of the analyte in any unknown sample. It can be a solid sample, or it can be a solution, or it can be a gaseous sample solubilized in some solvent, where we can go for this sort of reaction, where you all know when a particular base solution or a particular acid solution is completely neutralized, we get the typical end point of that particular reaction. So this is your unknown. So our analyte is unknown. So whatever analyte we have, where we see that an analyte can be a solid sample. From the very beginning what we are talking about, it can be a mineral or it can be a ore sample, or it can be a simple solution of any other metal ion, say Fe3 plus. So when you go for this particular reaction, that means you have an unknown analyte concentration, and that unknown analyte concentration should be consumed by the titrant whose strength is known. So known strength of the titrant will be utilized, and our basic intention is that you have to use up all the analyte present in this unknown solution. So we have to use up all the analyte concentration. So we will take some example of, say, typical titration. So a titration of, say, acid base titration. So if we take one such example where we can consider the titration of a acetic acid solution, say. So we are just going for acetic acid solution, and certain volume we have to take, say 50 ml to say 500 ml we can consume of, say, 0.02 molar concentration, and we want to titrate it with that of a solution of KOH, that means potassium hydroxide solution, and that potassium hydroxide solution of higher strength. So how we can get a plot where we see the corresponding change in the pH values. That means in this particular acid base titration reaction, how we can monitor the corresponding change in the solution pH values. Since we are going for an acid base titration reaction where we are starting from an acetic acid solution of certain strength, so we will be at the very lower level of this strength, that means between 3 and 4, the pH value will be between 3 and 4, and we will start from that particular point this titration, and on this axis we will be adding the milliliter of that particular KOH solution what we are talking about. So this is, say, 1.00 molar KOH solution. So milliliter of KOH. So, how the thing will change, therefore, that we will get a typical plot like this. So, we will just go like this, then we will have a sharp increase in the value, and then we will just see something. So, these are the points during the titration. So, once you add certain milliliter of that KOH solution, and we can monitor the pH change. So, if this can be the change, how we can utilize this particular reaction to go for a spectrochemical analysis, because all we know is that for a typical spectrochemical reaction where we should be utilizing some color reaction, but where from we get the coloration from this, because your acetic acid solution is a colorless solution, your KOH is also a colorless solution. Only thing what we are seeing is the only change in the pH. So, in this particular range, your pH will be dictated or governed by the corresponding pKa value of the acetic acid. So, this pKa value of the acetic acid will tell how far we can go during the addition of these KOH values. So, once we go this sharp rise, so this particular range basically within 1, 2 or 3 ml of the solution, your pH is jumping from say 6 to say up to 8 or 10. So, at this point basically, or this particular range when is going away, so this particular range, this horizontal part, this particular horizontal part is basically given by the corresponding pH of a chemical equilibrium what we have discussed so far, and we are talking about between the acetic acid and the acetate ion equilibrium. Okay. So, is HOAC and acetate ion equilibrium. So, we know the pK value of the acetic acid, we know the corresponding concentration of these acetic acid and the acetate ion, because after addition of this KOH we will be producing certain concentration of these acetic ion in the solution. So, but this particular line, so this can be your the change in the pH, where the change in the pH values can take place, where this acetate ion what is forming over there and the hydrolysis of this acetate ion will dictate or will control or give us the corresponding pH value for this particular reaction. So, pH will be given by the acetate hydrolysis reaction and will be given by the KOH, as we all know, which is nothing but your Kw by Ka value. So, this particular value will tell us this one. Then once we reach over here, so the vertical line we are finishing, we are completing the vertical line, then again we are approaching to some horizontal part of the graph. So, this horizontal part is then you have a very slight change or a very small change in the pH value after the addition of this KOH. So, milliliter addition of this KOH beyond the end point of this titration will be dictated by simple this pH also will be described by your water hydroxide ion equilibrium. So, after at the end basically when you are forming this water from the reaction of your base and the acid, we all know we are forming salt plus acid, salt plus water. So, this water will be there and we have certain amount of hydroxide due to this addition. So, this range of pH will be governed by this particular equilibrium. So, what we see basically from all these examples, that whatever thing we are doing, we are talking in terms of certain chemical equilibrium and then the control of the corresponding pH, which is again related to the pKa values by the Henderson-Hasselbalch equation that we have seen so far, and ultimately we are talking of something in this particular range where is a sharp change or is a jump in the corresponding pH values. So, how we can monitor this particular jump in this pH values, that we will see with the help of a direct titration or with the help of some spectrophotometer. But if we can have certain combination, that if we want to titrate a sodium carbonate solution with some acid, say hydrochloric acid or sulfuric acid. So, there if we see that if we start from a very high pH value, because this can be a very useful example where we can monitor not only the pH, that means the pH metric titration we will see, but also it can be controlled or it can be utilized by the corresponding potentiometric titration. So, there as you see, if we start from your sodium carbonate solution which has a very high pH value, and since we have two step of this protonation reaction, so we will get a plot like this with respect to the volume of acid added and the change in the corresponding pH. How the change in the pH? So, pH in this particular case, either you go from this way or you can go down from here. So, as you move this, so how the pH is changing from this particular case. So, there also you have the corresponding horizontal ranges as well as the vertical points. So, two such vertical points are there, where we can see for this particular one where the corresponding acid is your carbonic acid H2CO3, and it can have two pK values. So, we consider them as pK 1 and pK A2. So, these particular thing will then therefore, how to detect these two values, which is an important thing therefore. So, when we go for this determination or the titration of say carbonate ion. So, this particular titration is a very useful one, and we can consider a corresponding titration for any such diprotic acid like this particular carbonic acid or any other organic acid, that will stay the example. So, during this process, so one such equilibrium process will be there for the horizontal one. So, these horizontal positions and these three horizontal positions will be there, and this will be controlled by the corresponding equilibrium concentration of carbonate ion and the bicarbonate ion. So, the equilibrium between carbonate and bicarbonate will dictate the corresponding change in the pH value in this horizontal position. Then the pH in this particular range will also be governed by bicarbonate ion in the next step to your free carbonic acid. And lastly, like that of our H2O and H3O plus, because ultimately whatever acid we are adding, then the volume of acid addition will give you the corresponding H3O plus. So, these determinations are very easy to do and all these things, but ultimately what we are getting for all these reactions, your water plays some important role. So, water can show some leveling effect we call, and that leveling effect is known as that if we have an acid and that acid strength is higher than that of our water. So, any acid which is more acidic than your H3O plus species will donate the proton to water. So, if you have the acid, so if it is higher than that of your H3O plus, so any acid whose acidity is higher than that of your H3O plus will donate the proton to water. So, it will be donated to water, giving rise to all these H3O plus. Similarly, any base which is more basic than HO minus the hydroxide ion which is derived from the water will take off the corresponding proton from the water molecule. So, it will form more and more hydroxide ion from the water molecule. So, water can function, water can play the dual role of accepting the proton and donating the proton to the system. So, that is why all the time whether we are going for the acetic acid titration with KOH, or we can do for some titration where we can see that water can be protonated by the addition of the acid during your carbonate titration. So, we will be forming more and more the hydronium ion. So, these particular things, so when we go for these two changes, and basically the final plateau, the plateau is here, the second plateau is here and the third plateau is here. So, this plateau is the final plateau in this particular case. So, the final one is governed by the corresponding equilibrium of your water. So, is H plus plus HO minus. That is why you see that this particular thing, that means it can take off or you can give due consideration of the corresponding H plus and the hydroxide ions. So, if you have a strong acid compared to your water, it can donate that proton to this water molecule, and if you have a strong hydroxide ion based base which is stronger than the hydroxide which can be liberated from your water molecule, we see that we can extract this particular proton from water also. So, that basically sometime we will see that how this leveling effect can control the corresponding titration reaction. So, one such example in this regard we can see is the corresponding diprotic material which is your salicylic acid. So, one such example is our salicylic acid, where with that of the phenyl ring your attachment for two groups, one is the phenol function, another is the carboxylic acid function. So, definitely their pK values are different. So, this is more acidic compared to your phenol unit, and how to check or how to compare and how to determine the corresponding purity of this particular species, because we all know is a very good ingredient for preparation of aspirin molecule. So, aspirin molecule is nothing but if you go for the acetylation of the salicylic acid, is the corresponding acetylation of this hydroxy function of this salicylic acid will give you the corresponding aspirin. So, if we consider that this is stronger, so if you have a pKa1 is equal to 2.97 and this pKa2 like that of our carbonic acid, we have one pKa1, another pKa2. So, this is 2.97 and this is 13.40. So, to determine the unknown concentration of salicylic acid for the preparation of aspirin, we should know the corresponding purity of the bulk salicylic acid what is available for the conversion of this particular molecule, the salicylic acid, to aspirin. So, what we will see, since this carboxylic acid part is giving rise to a pK value of 2.97. So, we can monitor this particular group consumption with that of your sodium hydroxide or potassium hydroxide solution. So, we will titrate for this function only, this carboxylic acid function we can titrate. That means, we will go for only neutralization of this carboxylic acid end, not like that both the two ends of these we can monitor. So, this with the determination of this amount of carboxylic acid found for a sample of salicylic acid will tell us the corresponding purity of this salicylic acid for the preparation of aspirin. So, this is typical manual titration using burette pipette and the conical flask, but if we can substitute this particular thing, that means always we see that there will be a competition between this manual titration. So, what we can have a manual titration versus that of our instrumental methods. So, in this class of the spectrochemical method, we just slowly moving towards the methods what we can use for instrumental methods of analysis, but still this particular one, this manual titration is still a very good methodology where we can titrate the amount of these unknown samples starting from your acetic acid, this sodium carbonate solution or carbonic acid or salicylic acid. These are some typical examples. So, how we can utilize this for a real life application where we can go for analysis of wastewater during the corresponding pollution of air sample. So, we all know that industry is producing, for any industrial process we can we basically produce certain amount of wastewater depending upon the corresponding treatment what we do for the corresponding industrial process. So, if we see that some of our this wastewater, so this wastewater can be treated, that means treatment of wastewater is required before we just throw away this particular wastewater to some natural source or say river bed or ocean, all these things. So, the titrations can be used together, that means if we can have for a sewage treatment. So, the sewage water you can have. So, the sewage treatment, so for a particular sewage treatment what we get, that sewage treatment we can do where large amount of the fatty acids are there which are volatile. So, if the sample or if the sewage is containing some volatile fatty acids and this volatile fatty acid is basically allowing or taken in a particular reactant. So, this particular reactants can be given to a reactor. So, what are those reactants? Reactants are nothing but some bacterial degradation we can do. So, anaerobic bacteria we can use. Why we are using this anaerobic bacteria? Because anaerobically we can degrade the whatever organic matter is there. That means, if we can have this organic matter, that means the industry which is involved for doing this particular industrial process, they are handling some amount of organic matter, and these organic matters when they are fermented, they produce large amount of bicarbonate ions in the form of carbon dioxide. If the medium is alkaline, we all know that alkaline medium can consume carbon dioxide giving bicarbonate anions. So, how to determine these two things together? So, in a continuous process of doing all these things, that means if we go for the degradation of this organic stuff, what we can do that in this medium you can have both carbonic acid anion, that means the bicarbonate anion, and the corresponding volatile fatty acids, and these fatty acids can build up in the medium. So, when we treat it, so during the last stage of this fermentation process and anaerobic bacterial degradation, what we see that at the end basically we will be looking for the production of methane and fatty acids. So, these fatty acids can also be titrated. So far we have seen that the neutralization reaction can be utilized for the titration of volatile fatty acids, and when these fatty acids are getting degraded, we produce certain amount of these bicarbonate anions. So, when we have this particular thing, that means when more amount of these volatile fatty acids are producing in the medium, instead of this particular bicarbonate anion, because this bicarbonate anion production is giving rise to a buffered medium. So, that buffered medium can be consumed if we consume more and more of this carbonate buffer medium by the elimination of these volatile amino acids. So, during this process of this degradation, what we can do, that if there is a huge drop in the pH values due to the production of large amount of these volatile fatty acids, the system will collapse. So, this particular, that means the volatile fatty acid formation of this volatile, large amount of this volatile fatty acid formation will grow for drop in pH values, and as a result this particular reaction in the reactor will fail. The system will therefore fail. So, what to do? Only we can go for detection of this particular pH. So, this particular only pH determination, that means if we just simply look at the only pH determination of this medium, will not help us, that there is certain degradation due to the corresponding change in the pH of the medium, or certain amount of this volatile fatty acid is forming over there. So, only pH determination will not help us a lot. Instead, what we can do, we can determine in this particular case, that is why is a very useful use of the typical titration reaction, that we can go for the determination of both this particular volatile fatty acids. So, determination of both volatile fatty acids and bicarbonate is needed. So, that is why this particular one is only pH metric titration will not help us. So, we have to go for the corresponding determination of these volatile fatty acids. What we see, that this particular treatment, the last stage of this Swaraj treatment. So, at one end we should go for the corresponding, we should have certain procedure where we can go for this particular volatile fatty acid determination as well as bicarbonate determination. And as we have seen that these two things we can very easily handle. So, these volatile fatty acids, suppose it is from C2 to C6 fatty acids. So, fatty acids containing 2 carbon to 6 carbon centers. So, this as well as the bicarbonates we can have this as HCO3 minus or H2 CO3 or CO3 2 minus. So, total quantity of these carbonate species, the bicarbonate species and the fatty acids we can determine by this titrimetric method. So, sometimes this simple pH determination will not help us much. We should have certain amount of other things to do, so that we can have a very good idea about the quantity of those individual species which are forming in this particular medium. So, when we use this particular methodology, we can use the spectrophotometer And in this particular case, when we go for the spectrophotometer, we will be seeking answer for different titration results or the different titration methods. So, if we can have some titration, and that titration we can do by a spectrophotometer, what we can get, that we can get some answers. We must have some answers for some questions. So, what are those questions? That means a particular thing what we can answer is that if we have some weak acid, and that weak acid, how we can level that particular weak acid for a particular pK value. That answer how we can give. That means the weak acid is your acetic acid. How a titration can give you a result for the corresponding strength of the weak acid or the pK value of that particular weak acid using the Henderson-Hasselbalch equation, that at which particular pH range it can remain as in the acidic form or in the basic form, and how these two forms, that means the two corresponding equilibrium concentration of the free acid as well as its corresponding anion can control the corresponding overall pH value of the medium, that we will see. So, if for a real life example, if we can have like that of our white vinegar, we know that white vinegar if we can have, and the question in our hand is that what is the corresponding concentration, what is the concentration of acetic acid in that particular vinegar solution. So, that we can use. So, if we have a commercially available white vinegar in a hand, we can determine the corresponding concentration of this particular sample. Then we can have some pharmaceuticals. So, pharmacists or the pharmaceutical industry will also be interested to know for any pharmaceutical preparation to check its purity, and during the preparation ultimately the yield of that particular preparation. That example we have seen just now regarding the preparation of aspirin from salicylic acid. Suppose if you can have certain other pharmaceutical preparation where some iodine is present. So, not that the simple acid like salicylic acid. So, we have to use this particular ingredient in the pharmaceutical preparation by some titrimetric method. So, what we see from the titration plot or the titration curve, that we must have some endpoint, and that endpoint we have to detect, because at the neutralization point what we see, if we have a strong acid strong base titration, the pH, the final pH at the neutralization point will be close to 7, as we all know, because whatever salt is forming, so that salt will not interfere the corresponding pH value for a titration like hydrochloric acid HCl with that of our sodium hydroxide. So, these we all know that how the pH is changing, but when we are handling two colorless solution, your acid is colorless, your base is also colorless. So, handling these two solutions, how we can detect that particular change. So, when we see that there is a change, a sharp change like this. So, as we change, as we go from, this is the volume axis and this is the pH axis. So, when there is a sharp change and we just only focus our attention over here. So, at this particular range, how we can detect this particular change? The simplest possible answer is that if we can have a corresponding instrument which can detect the change in the pH during the volume of addition of some corresponding titrant, because this is your titrant, this is your analyte volume. So, pH can be monitored very nicely with the use of a pH meter. We all know that the hydrogen ion concentration in presence of the hydrogen gas and all these things is the electrochemical thing can happen, and we can have a glass electrode type of thing, and that glass electrode type of thing can determine the corresponding pH of that particular medium. So, this particular pH meter can measure the corresponding jump in the pH at the end point. So, this particular pH, this jump, so this is nothing but your jump in pH. So, we have to detect that particular jump in the pH value at the end point of the titration. So, how another alternative method we can use without using the pH meter, because this pH meter can be switched for the corresponding millivolt also, that give rise to our potentiometric titration, which is nothing but potentiometric titration. So, a very small instrument like that of our pH meter we have to handle to monitor this pH for a simple acid base titration. But what indirectly we can do, how to detect this particular change, whether we can go for this, and our basic choice is for utilization of the spectrophotometer. So, once we are talking about the spectrophotometer, we should be thinking something for any reaction or any change in the corresponding color. So, we will be looking for some color reaction, and whether this particular color reaction can be helpful to detect the end point of any titration reaction, and that color can be measured by a typical spectrophotometer. So, that we will see in our next class. Okay, thank you very much.